Hello, we are the Carrier Mist team, and this is our senior design project video. In this video, we'll go over the evaporative cooling project given to us by Carrier and how the team used thermodynamic calculations to design, manufacture, and implement the system. We were required to design, build, and test an evaporative cooling system for the Carrier 30XV air-cooled chiller. The system had to use finely atomized, filtered water to cool the ambient air at the intake of the condenser. This eliminates the opportunity to damage the condenser's coils. The system should only activate when there is an economic benefit due to an increased efficiency, also known as EER. Before designing could start, calculations had to prove that implementation of an evaporative cooling system would show a tangible benefit. This graph displays the relationship between the increased efficiency that is caused by using the mist to cool the air and the amount of humidity already available in the air. On very humid days, very little evaporative cooling is possible, which prevents substantial increases in efficiency. Here, you can see an idealized estimation of net savings in operating costs per hour. This accounts for the cost of water, power for our system, and savings introduced by an increased efficiency. For example, on a hot 80-degree Fahrenheit day with 50% humidity, our calculations project savings to be around $2 per hour. An average yearly savings calculation was performed for 3 different locations to determine how differences in humidity across climates could potentially affect our savings. We can see Charlotte has relatively high humidity, thus only yielding around $7,000 a year in savings. These savings for Tucson, Arizona and Las Vegas, Nevada are also shown here. Notably, the arid climates have much lower humidities and increased potential for savings through evaporative cooling. In these scenarios, the system could potentially save upwards of $20,000 a year. This slide represents our system layout and how parts of the system will communicate with each other. Initially, there is a water supply that the system can connect to, which then leads to the pump. From here, the pump will be regulated with our Raspberry Pi and solenoid valve. The Pi will ramp up the variable frequency drive, which controls the speed of the pump. The volume flow rate of water is limited by the solenoid valve. In cases where there is little to no flow required, the valve can be used to alter the volume of water so as to not be wasted. From here, the water will enter 3 different types of filters. First, a sediment filter is used to remove the largest particles from the system. Next, a deionization filter to prevent corrosion to the condenser coils. And finally, a water softener that helps remove corrosive materials, such as calcium, after filtration. Water passes through a flow meter that will communicate to the Raspberry Pi just how much water is flowing through. The Pi will determine if this is an acceptable value. If not, information will be sent to the VSD or solenoid valve to correct the flow rate. Following the sanity check from the Pi, the water will be split into 3 even flows at a 4-way cross. These then split to 3 6-way manifolds. Each of these manifold outlets will connect to a nozzle that evenly sprays mist onto the condenser coils. This is the design our team ultimately decided will most evenly cover the majority condenser coil area with mist. A previous iteration was going to use sheets of aluminum, but it was challenging to follow through due to the design being too large and difficult to manufacture. For this reason, we decided to construct it from aluminum bars and steel strut channels. The array houses 17 nozzles on each side, which are evenly spaced to mist the most area possible. The plumbing was designed in parallel to ensure each nozzle sees the same exact pressure as the one before it.
The electrical layout of the system starts with the electrical box. This includes 2 Raspberry Pis, the LCD screen, the temperature and humidity sensors, and the VFD, which is powered by 120 volt AC power. The VFD converts this to 240 volt 3-phase power to drive the pump according to the control signals it receives from the Raspberry Pi based on the ambient conditions. Water flows from the pump to a flow meter to act as feedback to the control system. Then, a solenoid control valve prevents water flow when the pump is powered down, as our water source is pressurized city water. The water then travels through the 3-stage filtration described earlier, where it then atomizes through the nozzles to mist the condenser. The thermocouples attached to the condenser measure the effects of our system. The Raspberry Pi outputs 0 to 5 volts to the digital analog converter, which doubles the signal to 0 to 10 volts for control of the VFD. The temperature and humidity sensor as well as the flow meter are wired to input pins on the Pi to provide necessary information to determine the set points and for feedback control, respectively. The LED serves as user feedback for our preliminary alarm system. The straight centrifugal pump is mounted to a sturdy plate in order to give it stability during testing. The VFD is shown here, set to 50 Hz output during our bench testing of the pump. Here we can see a voltmeter being used to show the output voltage of the DAC in order to characterize the VFD response. The humidity sensor is shown here in a 3D printed case in order to better protect it within the control box. The breadboard configuration shows when the sensor was being characterized with a test LCD message shown on the right. This video displays the Python code, which takes information from the sensors and uses it to determine the set points according to the calculations conducted last semester, which it then uses to adjust the solenoid valve and pump speeds accordingly. The electrical box serves as a safe zone for all the electrical components. This includes the VFD, Pis, breadboard, and the temperature and humidity sensor. The box will have holes drilled into it in order for it to be mounted on the underside of the condenser frame.
Manufacturing begun during the second semester of senior design. This involved milling of the horizontal bars down to size in the machine shop. Following this, drill bits and a hole saw were used to puncture the bar for both fasteners and nozzles. Stroke channels were used as the base of the system, and another channel was added in the middle to prevent rotation. Machined horizontal bars were fastened to the frame, and rubber grommets are used to prevent slippage. The entire frame is approximately 8 feet in length and requires 2 people to lift it. Grommets are made of flexible rubber which allow for the nozzles to be held tightly in place. This is the completed design with the nozzles and piping system. The manifolds are mounted directly under the frame to reduce tension. This allows for flexibility of the PVC piping. During the first benchmark testing, the nozzles displayed the ideal spray pattern for the system. This testing was done with piping connections from a sink straight to the piping manifold. Here is the video. During the second testing, we were able to include the VFD and pump in order to control the pressure. Sadly, the nozzles did not properly atomize the water. Instead of a cone-shaped mist, the water exited the nozzle in a bubble-like shape. We believe that it was caused by leakage at the sink and at the suction side of the pump, but not caused by the addition of the needed hardware. With help from the folks at Carrier, the team was able to have access to the condenser to perform a dry fit. This allowed the team to make sure that the current design would properly work and give the team confidence to continue building and testing. Before the team could continue testing, the labs unfortunately had to close due to the current circumstances. With the closing of all labs, progression of the project had come to a halt. It was decided that the work not completed was to be documented for either Carrier or for another senior design team to finish. We were asked to break down what was left, assuming another team was going to take part of the project and how it should be structured. The breakdown of the members would be as follows. The mechanical members would continue testing and mounting the system to the 30xV chiller. The electrical computer members would integrate the needed solenoid control valve as well as create an efficient alarm system and to finish the coding between the two Pis. This semester may not have gone according to plan, but it has most definitely given us the opportunity to put our engineering skills to test. Thank you Carrier and UNC Charlotte for giving us this opportunity and letting us show you what we were able to accomplish.